Good morning, class. Today is November the 4th, and so this is the video for November the 5th. And we'll first go over the second quiz. Okay, so problem 1, the answer is B, because as we went through this in the review, if this is the atmosphere, that as the atmospheric absorption goes up, in order to keep the balance with sunlight, okay, because there's less going out into space, T has to go up in order to increase this amount, because more of it is getting absorbed in the atmosphere, because what is radiated out into space has to equal the constant sunlight hitting the Earth. So the answer was B to that one. Number 2, the answer was also B. Wind power is limited because of its intermittent nature. Meaning that there's enough resource availability, we went through that, to supply all the U.S. electricity, but because of its intermittent nature, which would require some sort of storage at some point, that's what limits how much wind power there can be. And so those are sort of 2 qualitative questions, and then we have somewhat more quantitative questions. So here you were to determine how many more solar panels you would need, and compared to if you tilted them at latitude, so here's the sun, all right, as opposed to doing that if you had to lay them flat, okay, and you were supposed to look at the insolation maps on page 84 and 85, that for this configuration for Delaware, you get the equivalent of 4.75 hours per day of full sunlight, whereas for this configuration, if you look at the map, you get the equivalent of 4 hours per day. And so 4.75 divided by 4, I mean, in case you have a little difficulty thinking of the so for this you're going to get a certain amount of energy. The energy is equal to 4.75 times the number of panels tilted. Okay, and you want that to be the same for laying flat, where if you lay flat you get times 4, so you get that n flat over n tilt is equal to 4.75 over 4, so n flat is equal to, and that's 1.19 n tilt. So you need 19% more panels in order to get the same amount, which is kind of an interesting problem if you wanted to extend it. The question is then, oh well, in a sense I can pack them in more here, and so if you weren't worried about the cost of the panels, you might decide that it's actually a better configuration because you can pack them in more. All right, moving along, number 4. Okay, you were supposed to take this IV characteristic, and you were supposed to determine the maximum power, and so basically the idea that this crossed at around 28 volts, and this crossed at around 10 amps. And so if you were to, for example, take 25 volts and 26 volts and 27 volts, you would find that roughly, okay, that point, if you took those products, that roughly that point would give you about the maximum. And so, kind of the idea was to look at the plot and sort of, make a little rule line and stuff like that, and figure out that at this point you had approximately, that's more like 25, 24, 9. You had approximately 9 times 25, or around 240 watts, if you went through that. And the point is that W is IV, and I know there were a few students that knew this but didn't do the calculation, and so it's sort of reading off of a graph and realizing that, well, that's not a maximum. Okay, so it's got to be less than 28 times 10, and that's not a maximum because it's got to be less than kind of 20 times 10, and so the answer is 240 if you look at the graph. Number 5, okay, so basically you had a car with ethanol, or 10% ethanol, versus gasoline. Now, we went through in the notes that ethanol has an energy content of 28,400 versus gasoline of about 43,000. That's right from the notes, BTU per kilogram. And so 10% ethanol would be approximately 0.1 times 28,400 plus 0.9 times 43,000, and that works out to, I don't have it written down here, but somewhere around, I can do it in let me get my calculator. So 0.1 times 28,400 plus 0.9 times 43,000, 41,500. Now, if you stopped there, you would get the right answer because basically you take that divided by 43,000 and multiply times 30, and that would give you then 41,500 divided by 43,000 times 30, 29. Now that's not really the right answer because ethanol is slightly denser. It's 0.79 grams per cubic centimeter, whereas gasoline is 0.7. Recall that water is 1 gram per cubic centimeter to give you sort of a reference. So if you introduce that correction, it's like 29.2. But the closest answer was C, and so if you didn't do that, you would still get the right answer. So it's basically a question to make sure you understood the energy content of the fuels. And then number 6, which leads us into our lecture today, you had the PV diagram, and we went through how in a PV diagram that sort of just drawing it like that. As you go through the cycle, okay, energy is equal to the integral of PdV, which is the area under the curve, and so it's the area under that line, okay, minus the area under that line, because on this part you're getting useful work from the vapor, from the gas to the piston, whereas this you're doing work from the piston onto the gas, and so you're losing energy. And so it's the area under this curve, and that's basically just a parallelogram. Okay, that's equal to 0.2 plus 0.34 over 2 times 1, or 0.3. And there were no units in the problem, so that was the answer. So, I thought it was a good set of questions. I forget what the average was. I did email that, I think. We can go over it in the chat class. I guess of all of them, I like problem 3 because it's kind of a real problem that, as a worker in the field, you might be faced with at some point, which is a client basically wants to put in a solar array and has, a flat roof, and so, wants to go through a couple of configurations and basically determine, well, okay, how much energy would he be getting with each configuration? How many more panels would he need in these two geometries? It's sort of a real world problem. And in using those insulation numbers carefully, gives you the right answer. And so, sort of an interesting homework problem then would be then to take what we did in the previous homework on tilting the arrays and packing them in and determining, well, how many more can you get if you lay them flat, and do you win then? So I'm thinking of handing that out as a homework. Now, of course, you can pack more in, but you have to pay for the panels, and so it's not clear economically whether it's a good idea to lay them flat in order to get more overall energy. All right, so that was the quiz, and now we're picking back up on heat engines, which sort of picks right up from problem 6 of the quiz, which I'll erase because we'll remember it's the area under the curve. Now the reason, heat engines, and in subsequent lectures we'll go through the different varieties. We sort of touched upon it before the quiz, but they take heat and they convert it to work. And I won't redraw a piston and cylinder because I'm going to draw it in a little bit here. But what we've seen, and okay, let me go ahead and over here put a PV diagram, an actual PV diagram. So without drawing the piston and cylinder yet, which I'll get to in a second, I mean, basically you start the cycle with the maximum compression of the gas, and you input heat, and so there's a part of the cycle where you're inputting heat. And so you're pushing the piston up, and so the volume of the gas in the cylinder is going up. Okay. And we're going to do the Carnot cycle. And so if you call this point 1 and this point 2, in the next part of the cycle, and I'll explain that in a little bit, the piston continues to go up, and so the volume underneath the piston continues to go up, but the pressure falls faster, and we'll explain why in a minute. But for the Carnot cycle, okay, the heat is constant. And then in the next part of the cycle, you extract heat. All right, and we'll explain, you know, how and why you do that. And then in the final part of the cycle, the heat is constant. Again. And so you have these sort of 4 points in the cycle, and this thing keeps going around in a circle like this. And that's your engine, up and down, up and up and down. This is the Carnot cycle, and we're going to analyze it a little bit. But now the point is, we want to know, for heat to work, what is the efficiency? That's what we're getting at here. It is useful, like for solar cells, to understand how engines work as an energy professional, and so it's a useful understanding to go through this. But there's a more important reason we're doing this, which is that we want to understand what the efficiency of an engine is. And I forget which homework it was, but in one of the homeworks we went through with the home generator, calculating that based upon the rated specifications of that device. You know, we determined that it was somewhere around 15%. Now, the reason why we want to know this is because, of course, right now, and for your final project, of course, we want to understand, if we take essentially a car with a gasoline engine in it, and we replace that gasoline engine with an electric motor, all right, how big does the battery have to be, basically? Because, you know, we know, or we assume that the engine or the motor has to supply the same amount of power to move the car. We need to know then the efficiency of each one. And we've already went through that the efficiency of electric motors is very high, and we'll explain that later in the course, somewhere around 90%. And so for our homework problem, we found 15%, meaning that's a big difference. And so this is the starting point of determining what that is, because there is something called a thermodynamic efficiency. Which is inherent in any heat-to-work engine. And where that comes from is because in order to get a cycle that has an open curve like this, there has to be a portion of that cycle where you output heat, and this basically goes, I mean, metaphorically down the drain, or out your muffler. That basically it's discarded as waste. So there has to be a part of the cycle where basically you're discarding heat in order to have an open curve like this. And while I'm not going to prove it, this Carnot cycle, and we'll go through the actual equations in a little bit, is the most efficient engine you can have, and we're going to calculate that now. So let's just get started. So what I'm going to do over here is I'm going to draw a piston and cylinder of a Carnot engine for each of the points, and so from 1 to 2. All right. All right, here's our cylinder. Here's our piston. And so for 1 to 2, it's moving up. I won't draw the crankshaft over here again, but we went through how this is connected through some mechanical linkages so it can turn a drive shaft that's going into the board. And from 1 to 2, well, actually, let me write it this way. At step 1, you put in hot water. At T hot. And so this is a made-up engine, but it's a way of describing how it works that in principle you could make. That at point 1, okay, which is where it's gone through its maximum compression point. At that point, you fill this bath instantaneously with hot water, T hot. And since the in this sort of hypothetical engine, the sidewall of the cylinder is a perfect heat conductor, then this is at T hot also. So from step 1 to 2, T is at T hot. And then in point 2, okay, let's draw our piston and cylinder. Let me try and keep them in the same positions so it looks nice here. So at step point, now look what's happening here, okay, on the curve. Okay, from 1 to 2 to 3, the piston is still going up. So we're at some position here. The piston is still going up at point 2. All right, and what happens is that at step point 2, we instantaneously drain the water. So at point 2, okay, our engine is designed so that instantaneously at that point, all the water is drained. And now what does that mean? Well, that means this thing is just sort of free running now at this point, okay? Meaning the piston is continuing to go up, okay, but there's no energy transfer to the gas in the cylinder. It's just sort of freely going up. And what that means is that the gas is expanding in this step without any heat input. See, from 1 to 2, it's kept at T hot because of the hot water, okay, which we assume is infinitely large, so as it's extracting heat, it doesn't matter, and it stays at T hot. And step 2 to 3, there's no heat input, okay, and so the heat is sort of constant, and yet we're expanding the volume, and so what that means is that the temperature is going down from T hot to T cold at that point. So, you know, very simple, from step 2 to 3, the gas is expanding, sort of free running without any heat in or out, and so the temperature has to go down, because if the temperature of expanding gas goes down. Then at step 3, okay, let's redraw our piston and cylinder again. Now at step 3, we're at the top. Okay, we've reached the maximum height, the maximum volume. And at step 3, basically, you instantaneously put in the cold water. So if we go back to our cycle here, okay, at step 1, when the piston was at the bottom, we instantaneously put in a bath of hot water so that gas started absorbing heat from that hot water. And it started expanding at a constant temperature because, you know, basically there's enough heat in that water that keeps that gas right at T hot. And then at step 2, we drain the water. If the piston continues to go up, the gas expands, and so because an expanding gas cools, it goes down in temperature, and it goes down to T cold. Now you may be starting to think, well, how did we know that it went down to T cold in that step, right down to the temperature of our cold water? Well, because we've designed it that way. All right, and we've designed this thing with some kind of computer that is controlling where where the piston is at a maximum, minimum, etc., so that everything fits together. So now basically it starts going down, right? And it goes down at a fixed temperature, T cold, because again the sidewall of the cylinder is so thin that it keeps that gas at T cold. So if you think about it, what's happening there is that the piston is now doing work on the gas, compressing it. All right, the gas is being kept at T cold, so basically there's a transfer of heat Q into that cold water. Basically, the cold water is cooling off the gas and extracting heat. All right, and then at step 4, all right, redrawer. Bigger. Okay. All right, so step 4, okay, we're still going down. All right, and what do we do at step 4? We drain that cold water instantaneously. Okay, drain. So what happens right at step 4, okay, and again, we've designed our engine this way. There's a computer running the whole thing, keeping everything going. Uh-oh, I lost my focus because let me see if I can get it back. That never works. There we go. All right. Okay. Okay. So in step 4, at this point, okay, we drain that water, and that's where our heat goes. That's our heat loss. Okay, because although we said that in this step from 3 to 4, that everything is kept at T cold. In fact, in reality, as we're extracting heat from the gas, that has to go up a tiny bit in temperature, and then basically, that's our drain, and that's our energy loss from the system. So that is a Carnot engine. And then basically, after step 4, it continues to go down. Now, as it's going down, there's no heat, back and forth. And so what happens there is it goes from T cold to T hot. Because as you compress a gas, you have to raise its temperature. So that's the cycle, and it's pretty easy, really. And you can see that now, let's go through. Okay, P of V. So from 1 to 2. Okay, from 1 to 2. Now what I'm going to do is I'm going to put off to the side here, right under thermodynamics, because that's where it belongs. The ideal gas law. Now I'm going to write it in a different way than you may be used to, just for shorthand. I'm just going to put beta there, T. So we went through this last time that pressure, that pressure is proportional to temperature, and proportional to 1 over volume. We started the course with that. Those of you who remember your chemistry in the actual ideal gas law, remember that within this beta here, there's Rydberg's constant and the number of moles of gas, but our cylinder is sealed, right? So the number of moles of gas is a constant. So beta is some constant that I'm just going to put in there for convenience for the mathematics at this point. Now, so from 1 to 2, the temperature of the gas is at T hot. So the pressure is equal to beta T hot over V. So it goes as 1 over V. All right, easy. Now, we're going to be doing an integral here in a little bit, and so you can see that that's an easy integral to do. Now, from 2 to 3, okay, now, pressure is always beta T over V, so it's still beta T over V. Let me see if I can make this a little bit better. Constant. All right, so from 2 to 3, all right, well, let me just jump ahead here. From 2 to 3, we said that the temperature was going down. All right, this is the one place where, the one step in the analysis where I have to just sort of tell you a result from thermodynamics, which is that we kind of know, I told you in the introduction, we talked about how the fact that if I compress a gas, I can't compress a gas without raising its temperature unless I hold it at a certain temperature. For the same reasoning, I can't expand a gas without lowering its temperature unless I fix the temperature or somehow. So I'm just going to tell you that from 2 to 3, the temperature is going down as 1 over V to the n, where n is some constant, less than 1. And that constant n depends upon what type of gas it is. And there's some more discussion in the notes. For pure air, it's like around 0.4. For helium, for example, it's 2/3 precisely. And this is there's some discussion in the notes where I try to sort of make up, some sort of hand-waving analysis of why this is the case. But, for the purposes of this course, I'm just going to proclaim that it's true and go from there. And so from 2 to 3, the temperature is going down, and it's proportional to 1 over V to the n. Now, let's think about that proportionality constant, okay? And I'm going to, in the interest of time, I'm gonna skip a couple of steps here at the video. Maybe tomorrow during the chat class we can sort of formally write it out. But basically, if it's proportional to 1 over V to the n, I can just look at it and write down that the temperature is equal to T hot times V2 over V, where that's V2. Now, why is that true? Because at V2, the temperature is T hot, okay? And so it all works, right? I know it goes as 1 over V, and I know it's T hot at V2. Now, this is very important, this next thing I'm going to write down, which is that, okay, I worked out my proportionality constant. I'm sorry, there's an N there. I worked out my proportionality constant. It's T hot V2 to the n, because at V2 it's equal to T hot. But it's also equal to T cold V3 over V to the n. because here, because at V3, at that point, it's equal to T cold. And so if I plug in V3 there, right, see what I'm doing here? It's going as 1 over V to the n, and I'm just sort of kind of skipping a couple of steps so that I can write down an actual equation instead of a proportionality, because I know at V2 it's T hot and at V3 it's T cold. All right, so now I know those things are true, and so I can pick either one of them, and I can write that P is beta T 1 over V, so it's equal to beta T, I'll put T sub C, running on a space here. Oh no, let me use hot, sorry. V2 over V to the n 1 over V. So if you think about that then, okay, I can bring out beta T hot V2 to the n 1 over V to the n plus 1. Right, because there's V to the n there. So I know what P of V is from that point to that point, and I've determined that, and it's sort of you knew ahead of time, because you know if the temperature is dropping, it's going faster than 1 over V, so that's going as 1 over V to the 1 plus n. So it's dropping faster than 1 over V because it's dropping as V to the 1 plus n, where n is something like 0.5 or something like that. All right, continuing here, from 3 to 4, okay, it's like up there, it's easy. P is beta T cold over V, because from 3 to 4, the temperature is T cold. Now, from 4 to 1, okay, same sort of deal. T is proportional to 1 over V to the n, right? Because, okay, it's going up now, all right, and so as V gets smaller, it gets bigger. And of course, it makes sense that it has the same relationship as far as n goes, because that's sort of, you know, inherent in the thermodynamics of everything. And so, again, I can write my actual equation as T is equal to, so at this point it's T cold, and that's V4. Okay, but it's also equal to T hot times V1 over V to the n. And so, you know, I mean, we could have spent 5 minutes, you know, doing a standard thing of going from a proportionality, you know, because then that means it's equal to some constant times that, and then basically plug in a boundary condition to solve for the constant. And I'm just sort of skipping a step here because, you know, it's just sort of I mean, it's just apparent, right, that since T is T cold at V4, that plugging in V4 here, that's T cold then, and it's going as 1 over V to the n, so it works. And it's also T hot at step 1, at volume 1, and so if I plug in volume 1 there, I get T hot. Okay, and so the same sort of thing happens here, and I'll just skip one step and write out, and I'll use the T hot one. Beta T hot V1 to the n times 1 over V to the n plus 1. And again, it's because T is going as 1 over V to the N. V is, of course, V. And so on an overall basis, here, it's going as 1 over V to the 1 plus N. And so, like in this step, it's falling faster than it fell during this step. In this step, it's rising faster than at this step, so it all connects. Now, I'm going to try and put everything on the board here. If you look at this, now, I wrote these equalities here, you know, and these equalities are based upon my assertion that at these points in the cycle, you know, that it's T cold here, it's going from T cold to T hot, it's T hot here, it's going from T hot to T cold, and that corresponds to these volumes, and that corresponds to these positions of the piston. Well, how does this all work? Well, there's some sort of mechanism that's controlling the drain and such, so that at those volumes, like at V, you know, it all fits together and it all works right, so that at V1 you introduce your hot water, at V2 you institute your drain, at V3 you institute your cold water, at V4 you institute your drain, and this thing just keeps going around and around. Now, how's that happening? Well, okay, one way is I could have a computer controlling the same thing, the whole thing. The other way is I could have some mechanical arrangement so that when it reached this volume, it would have some mechanical arrangement up here that would trigger the hot water to come in. Same thing for the rest of them. And in fact, jumping ahead to real car engines, that's exactly what happens, which is that in old car engines, you have something called the camshaft, as well as the distributor. And so basically in a car engine, as the piston would reach certain points in the cycle, there'd be either a mechanical or electrical trigger for the event that was supposed to take point at that time. And just like this can be computerized, most car engines today, instead of having those mechanical and sort of hardwired electrical control systems, have a computer deciding the whole thing. And which is why if your computer chip ever goes in your modern car, your engine basically won't work anymore. So, you know, everything is happening here and designed so that it obeys these equations. Now, notice this one and that one. And if you look at that, okay, these equalities mean, because look, if I set that equal, T hot V2 to the N is equal to T cold V3 to the N. Okay, that's from 2 to 3, and then from 3 to 4, I'm sorry, from 4 to 1, I have that, I'll write it this way, T hot V1 over N, V1 to the N, is equal to T cold V4 to the N. And so from those, I can write, and I'm getting scrunched up here, T hot over T cold is equal to V3 over V2 to the N. And I'm sorry, I scrunched up here, is equal to V4 over V1 to the N. So we can use that, and we will use that in our analysis, that those equalities are true. Okay, now we got all the information. Now we integrate into and so basically, net energy is these four intervals is equal to the integral, and I'll just write 1, 2 pdv plus the integral from 2 to 3 pdv. Now I'm going to do it sort of formally mathematically. Plus the interval, then of course these means v1 and v2, I'm just not doing it all. From 3 to 4, plus the interval, sorry I'm getting scrunched here, from 4 to 1. All right, now if you remember your math, you'll remember that when you flip these, right, because v4 is smaller than v3, and so the net energy is equal to the integral from 1 to 2 of pdv plus the integral from 2 to 3 of pdv minus, I'm going to flip these, the integral from 4 to 1, or from 4 to 3, sorry, of pdv minus the integral of 1 to 4. Let's get there, of pdv. And all I've done here is I've sort of formally mathematically written out that it's the area under the curve. And so I'm going to calculate this integral plus this integral, subtract this integral, and subtract that integral, doing the integral like from here to there, so it's a positive value. And we can enter all those. From 1 to 2, okay, it's beta T hot over V dV. From 2 to 3, okay, it's beta T hot V2 to the N times dV over, over V to the N plus 1, or I'll write 1 plus N, minus, from 2 to 3, it's easy again, so this is from 2 to 3, sorry, from 4 to 3, beta T cold over V dV, and then I'll scrunch this over here, the integral from 1 to 4 of T hot beta. I planned this out just so it would fit on the board. You know what I did? Okay, do this. Okay, change those subscripts so it fits better. Okay. Actually, I can fix it even better. Right, because I should have done that to begin with. So T hot over T cold, right? Well, actually, no, I wrote it out. Let me write it out. T hot V2 to the N is equal to T cold V1 to the N, and from here, T hot V, whoops, let's see, that should be 3, sorry. T hot V1 to the N is equal to T cold V4 to the N. And you put those together to get that. And then I can write my thing here. From 1 to 4, beta T hot to the N, or T hot V1 to the N, using this one, times dV over V to the 1 plus N. Sorry, it's all scrunched, but it's there. So this is what we're going to do next time. We're going to do those intervals. Now, it looks hard. Okay, but it's not really if you think about it. The only tricky part is this, really. That's the only part where, you know, we have to, see, I didn't, you know, for the chemical engineers in the audience, or mechanical engineers, I didn't do any, like, entropy or anything weird here. I mean, I'm calculating the energy this engine is delivering, and then I'm going to calculate what its efficiency is from that. And all I had to know, where is it? All I had to know, well, we'll pick one over here. All I had to know is what I told you in the beginning of the course. The very first equation in the course. Energy is force times distance. Okay? And I proved that by deriving kinetic energy is 1/2 mv squared. All right, so, you know, all I had to know was the very first equation from the course. Energy is force times distance, which means it's force over area times delta volume, because the A's cancel out. All right, so you knew this, all right, from basic physics, basic mechanical physics. I didn't have to, you know, do any strange thermodynamics to do this. And you know, of course, the ideal gas law was something you had to know. That's from basic chemistry. And so the only part where thermodynamics comes in is here. That when a gas is expanding or contracting, its temperature goes as 1/v to the n, where n is a number less than 1. And it's useful, you know, to try and prove that. I try to offer some qualitative guidance in the notes. For purposes here, I just want you to accept that that's true, and sort of commit it to memory. And once you have that, this looks complicated. Okay, it's not, you know, math, you know, engineering derivations aren't like this, aren't hard. I mean, I guess complicated is the right word, complex is the right word, but the math of each step is very simple. And next time when we do the integration, you know how to integrate 1/v. You know how to integrate 1/v to the 1 plus n. This always gives me trouble because, you know, the rule, you take a derivative, you know, x squared is x, you know, that sort of thing. But when it's in the bottom, negative numbers always give me trouble. But, you know, we know how to do that integral. And of course, these are the same things again here. Now, so this is, you know, the one kind of intuitive step that you have to commit to memory. A temperature of an expanding or contracting gas in the absence of any other controls or any other heat sources or anything like that will go as 1/v to the n. And now, and then we use this plot, this cycle, to show this over here, which I hope is showing up on the, let me just see if that's showing up on the screen here. Yes, it is. T hot over T cold, you can barely read it, but it's there, is equal to V3/V2 to the n, which is equal to V4/V1 to the n. It's barely there, but it's there. And we're going to use that and do the integrals, and we're going to compute this next time. So I'm going to end the class there, and then next time we'll do the integrals. I will assign homework where you have to, you know, do this yourself. And again, it's not hard. You know how to do these integrals. You know how to set up the problem. Okay, it's just thinking it through, one step at a time. It's not hard. Okay, so we're going to end there, and we'll talk about it tomorrow.